So my screen now is showing the periodic table of elements from the website of RSC, which is Royal Society of Chemistry. And here you can see the trends in the periodic table. We have the vertical arrangement and the horizontal arrangement. The vertical arrangement we call the groups. So this is the first group and the second group. Yeah, the first group includes hydrogen and the rest of the alkali metals. They have one electron in their outermost s orbital or s subshell. They are soft, highly reactive, and the reactivity normally increases down the group. The size of the atom also increases down the group, with the hydrogen being the smallest and the francium Fr being the largest. Now the second group here, or group 2, they are called the alkaline earth metals. They are also reactive, they are harder and denser. And the group 2 elements, they also have electrons in the outermost s orbital or subshell, and therefore these two, they are called the s block, also including the helium in the 18th group. And then we also have the P block over here. The P block consists of elements that outermost electrons are in the P subshell or P orbitals. Don't forget that P subshell can hold maximum of 6 electrons. This consists of group 13, 14, 15, 16, 17, and 18. Now, group 14 also consists of several metalloids, for instance, silicon and germanium. So metalloid is the elements that are in between the metal and non-metals, as you can see here. Yeah, metalloids are elements with properties that are in between those of metals and non-metals. You can also click up here for metal. So these are all elements with metallic properties and also non-metals, and mostly they are in the P blocks. Now we have the D blocks right here. D orbitals can hold a maximum of 10 electrons in 5 distinct orbitals, and these elements, we commonly know them as the transition metals. It's from group 3 up to group 12. Okay, D block. The D block contains metals that are typically hard and dense, and they are good conductors of heat and electricity. They are, however, less reactive than the S block metals, and they often form colored compounds. And then lastly, we have the F block, which consists of 2 rows over here. Yeah, we have the lanthanides and we have the actinides. Now, the F blocks indicates the outermost electron of these elements being in the f orbital or f subshell. Now the f subshell consists of 7 orbitals, and therefore they can contain up to 14 electrons. Okay, so that was the groups, the vertical arrangement, and now the horizontal arrangement that we call the periods. This is the first period. Yeah, first period contains hydrogen and helium. They are both colorless gases. Yeah, they have electrons only in the s orbital. They only have one shell. Yeah, the second periods, they have 2 shells. Contains 8 elements. And then the third one contains 3 shells, and so on. Now going down the periods, the size of the elements increase. That's the trend for the size. Now in this table, you can also check, for instance, if we increase the temperature here and we get more or less the room temperature, which is around 27 degrees of Celsius, you can also see their phases. So most of the elements in nature, whether they are naturally occurring or they are formed in nuclear reactors, they are solid. Yes, you can see in light blue color. Some of them are also liquid, like the bromine Br, the Hg, which is the mercury, and Fr, yeah, which is francium. And also some of them are gas. We can see them in green over here, and some of them are also unknown because they are not very stable. So from this particular table you can learn a lot. So you can also click on the table, as you can see in here, like fluorine. It has several facts, including the electron configuration that we're going to talk about very soon, and then the use and properties, and also history, and of course atomic data. It's also very important, and so on. So you can also check this rsc.org web to it's also interactive web to learn more about elements. Now let's discuss the electron configuration in an element. Electron configuration means the arrangement of electron in different orbitals in an element. Now if we have very simple element or atom like hydrogen, which only has one electron, of course the configuration will look very simple, which is 1s1. This codes for the number of the shell, or what we know as the principal quantum number. This is the orbital, which also correlates to the azimuthal or angular quantum number, and this is the number of the electron. So we have one electron in the orbital of 1s. However, things get complicated very fast when we have more complex atoms, when we have atoms with more than one electron like this, and even more than, for let's say 20 or 30 electrons. Now when we have an atom with a lot of electrons like that, obviously the electrons, they are going to fill more than just the s orbital. Therefore we need a guide to be able to fill in all of the electrons in suitable orbitals. Now, the rule of filling in electrons in different orbitals, especially for atoms with multiple electrons, is described in the Aufbau principle. So in this principle, electron will first fill the lowest energy level and then moves up to the higher energy level. And we have described before that in the first shell you only have the s orbital that we write down here as 1s. In the second shell we have 2s and also 2p. Of course, this px, py, pz, although the order does not matter because they all have the same energy level. In the third energy shell, we have 3s and 3p, and also there's 3d, which is the energy of 3d is just a bit above 4s and then below 4p. So the sequence of filling in electrons in orbitals goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, and 5p. Let me write that down for you. So it goes 1s, and then 2s, and then 2p, and then 3s, and then 3p. But before we move to 3d, actually 4s has lower energy than that. 3d, 4p, 5s, 4d, and 5p. So this is the sequence of filling in electrons. Of course, first we need to fill in the lowest energy level. So if we have 2 electrons, then both of them are going to go here. If this is full, then we move here. Maximum 2 electrons, and this one maximum 6 electrons. 2, 6, 2, 10, 6, 2, 10, and 6. Okay. In this figure, you can also see the maximum number of electrons in each shell. The first shell or first energy level has 2 electrons maximum. The second one has 8. Third one has 8 as well. The fourth one has 18. and the fifth one has 18 as well. If you remember the periodic table where we have the arrangement of periods, the number of the maximum electrons in each shell is the same with the number of elements in each period. Say for the first period, we have two elements, which are hydrogen and helium. And then for the second period, we have 8 elements. For the third period, we have also 8 elements. For the fourth period, we have the transition metals here as well. So we have 18 elements. And for the fifth periods, we also have 18 elements. As you can see, the first period has 2 elements. The second period has 8 elements. The third one has 8 elements as well. While the fourth one now, we start to fill the d orbitals, which is 3d. Yeah, so we have 18 elements over here. For the fifth one, also we have 18 elements. For the sixth and seventh period, we also have the F blocks. Yeah, so this what we call the Lanthanides. It's basically stacking on top of this element right here, and we also have the Actinides, which is the seventh period, which is also basically these green ones. They basically stack on top of this actinium number 89. Now let's take one of these examples to write down the electron configurations. I'm going to take, for instance, phosphorus right here, number 15, and manganese, number 25. For phosphorus that has 15 electrons, we can write it down from 1s2, and then 2s2, and then 2p6. And this makes up 10 electrons, so we need 5 more. So then we can fill in 3s2 and 3p3. So according to this, we can see that the valence electrons for the phosphorus is over here in the latest or in the outermost shell. We have 2 electrons in the 3s orbitals and 3 electrons in the 3p orbitals. And from the number of the shell in here, which is 3, we can relate this to the period number for phosphorus. So phosphorus should be present in the third period. We can check here that is indeed phosphorus present in 1, 2, 3, which is the third period. Also for the groups, we take the valence electrons, and in this case we have 5 valence electrons, 3 plus 2, and the 5 valence electrons correspond to the phosphorus being in group 15, as we can see in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So phosphorus number 15, it's in the third period and in the group 15. Okay. Now let's take another example, which is manganese. Manganese of atomic number of 25. So we can write it down like this: 1s2, 2s2, 2p6, 3s2, 3p6. Yeah. And up to this point, we have how many electrons? 18 electrons. So we're lacking 7 more. We have to put 7 more electrons. And in this case, of course, then we're going to move to the 4s. 4s has 2 electrons as well. Now we have to put 5 more electrons, right? But in this case, don't forget that after 4s, we don't move to 4d. Instead, after 4s, right here, we start with 3d because 3d has a lower energy than 4p. And also, after 3p, we don't move to 3d, but we move to 4s because 4s has a lower energy than 3d. Yeah, that's why after 3p, right here, we start with 4s, and now we start filling in the 3d. So 3d here is the remaining electrons, which is in this case 5. Okay? Now this again, is the configuration of half-filled, meaning that this will increase the stability of manganese due to the orbitals being half-filled. Now, sometimes we can also write the shortened version of this electron configurations, because 18 is actually the number of argon right here. So these are what we call, I haven't told you this, but I'm gonna write it down right here. The group 18 is what we call the noble gases. Noble gases are known to be not reactive. Mostly they're not reactive, and they are called noble because they are very hard to react and they are relatively stable. So in this case, argon is number 18. We normally use the noble gases to shorten the electron configurations for other elements. Therefore, we can also write down the electron configuration for manganese as AR, which is short for argon, PS2 3D5. It's the same with the lengthened version like this. Now let's take another example. For instance, take chromium. Let's take chromium number 24. 24 chromium. It's gonna be the same with this one, just lacking one electron. So it's gonna be AR 4S2 3D4. Now here you have to be careful. Because the actual configuration for chromium is actually this one, AR 4S1 3D5. Okay, so it's not this one, not the upper part, but this one. And that is because in this configuration below, you can see that we have a half-filled configuration. And this half-filled configuration, as I mentioned before, they increase the stability. So the chromium will prefer to be in these configurations. The electrons of S over here will move to D in this case to make D half-filled, and the S will also become half-filled. So be careful for some of the elements like chromium right here. You have the half-filled configuration because this will lead to a more stable element.